Dear friends, I invite you to the next episode of the Smart Methodology podcast. This time, we are diving into one of the most relevant topics of our time, artificial intelligence. And I am proud to introduce our next guest, Dr. Bernd Kleimt from BFI Germany. Dr. Kleimt and BFI take a part in the project co-founded by the European Union, and Dr. Bernd Kleimt is a leading expert in the field of digitalization and the implementation of artificial intelligence in the steel industry. I had the opportunity to see Dr. Kleimt's presentation at a recent conference, and it left a lasting impression on me. Now you have a unique chance to watch this presentation online. But before we begin, let me briefly introduce the company behind this podcast. I am currently leading two projects, Smart Scrap and Smart Metallurgy. Smart Scrap is a global trader of metallurgical waste. Right now, we are in the process of transforming the company into a full-scale recycling operation. We are negotiating slag processing projects in several countries around the world, and we are actively looking for investment partners. If any of our listeners are interested in learning more about these projects, feel free to reach out. We would be happy to connect and talk further. In our second project, Smart Metallurgy, we help electric arc furnace plants improve their operational efficiency. My colleagues will now share links to our website in the chat, so where you can learn more about who we are and what we do. So, Dr. Bernd, it is your turn. You can start.
Yes, thank you very much, Mr. Korablin. Thank you for inviting me to this presentation. First of all, I would like to introduce myself. My name is Bernd Kleimt. I am working since 36 years for the VDEh-Betriebsforschungsinstitut Düsseldorf, Germany, which I will introduce to you in the next minutes. And my core activities are the liquid steelmaking processes, and for them we are developing measurement technologies and also dynamic process models to improve the monitoring and control of the processes. And since several years, I'm also focusing my work on scrap characterization and scrap use in electric steelmaking. So my today's presentation, I will go to the presentation mode first. Today's presentation, I will first give you an overview on the VDEh-Betriebsforschungsinstitut, and I will describe the activities of BFI, the field of metallurgy. Then I will describe with a strong focus the Horizon Europe project s-X-AIPI, which I will describe to you in much detail, and also the results which we have achieved in that. And I will just briefly tackle further European BFI projects on use of artificial intelligence methods in metallurgy. So, well, first of all, a short presentation of BFI. So we are Institute for Applied Research, and we are focusing on these four topics which are very relevant for the steelmaking industry. It is CO2 reduction and energy efficiency, digitization and process measurement, circular economy, which of course tackles also all the steel scrap topics, and process optimization. So our institute is located in Düsseldorf, Germany, and besides an office building, we have also an experimental hall where we can perform pilot plant trials, and we have a big laboratory for chemical investigations regarding water treatment. So BFI is a non-profit institute for innovation with a focus on applied research and development. So we are a private institute, not a university. So we perform innovation as well as short and medium-term research work, driven always by the demands of the industry. Our key areas are the plants, the processes, and also holistic systems. We are not performing any material science. and we are embedded in a large national and international network with other research institutes, but also with our industrial partners. We are performing bilateral research. That means for only one industrial partner, but the most important part of our work is funded research projects on an international basis with other partners in Europe. Then we have some services like measurement campaigns and industrial projects and licensing of patents. We have approximately 100 employees. 70% of them are academics and postdocs. So you can see the breakdown of the BFR revenues, which also gives a clear view on the focus of our work, which is clearly on the research projects. We receive around 50% of our budget by research funding. But on the other hand, we have also a strong participation of the industry in these projects by direct client participation or by contract research and services. And then we have some basic funding from our mother, the VDEh, and some license income. So we are dealing with a lot of partners, not only in the steel industry, but also in the chemical industry or in non-ferrous metals industries. You can find all the industrial companies on the left-hand side. And on the right-hand side, you see the partners from the plant suppliers, from the companies developing measurement systems or process control software systems. So we are also embedded, as I said, in a European steel research network. All over Europe, you will find research institutes which are focusing on metallurgy and process optimization. So with all of them, we are performing joint research projects and have a very intensive contact. Besides that, we are in contact to the universities in Germany, which are dealing with computer science, process management, mechatronics, metallurgy, and so on. So regarding our 4 fields of activities, I would like to show you for each of them only a brief snapshot what we are doing in these fields. So this is only very quickly to give you an overview. Regarding process optimization, we are performing our work with physical models. This can be water models or even pilot plants installations. We have a strong focus on CFD simulation and other process analysis methods. We are dealing with corrosion protection issues, with texture optimization. We have a big experimental hall where we can perform reduction experiments, and we are developing assistive and decision support systems based on software solutions which are developed by our own. Regarding decarbonization and energy efficiency, we are developing systems for heat recovery, for optimization of industrial furnaces. Optimization of industrial furnaces, metrological recording of energy mass balances, waste heat utilization, and also hybrid heating system of thermal processes. Please excuse the short disturbance here. So main focus is on burner systems. For example, we have a system where we can optimize the burner operation, which is used in electrical furnaces, for example, but also in reheating furnaces. Yes, then coming to digitalization and measurement technologies, here I will focus on the measurement systems which we are developing. So we have a strong focus on optical measurements, for example, for optical fibers for temperature measurement. We have different measurement technologies for the blast furnace optimization, particle concentration in fluids, and a non-contact diameter measurement, as well as a flatness and temperature measurement system has been developed by BFI. And last but not least, the circular economy. So besides all the topics dealing with scrap, we are also performing work regarding other residuals coming from the steel plants, for example, scales or dust and sludges. And here we are developing agglomeration and pelletizing processes to use these residuals in the liquid steel making. So utilization of process gases is an important topic. As well as gas cleaning and gas separation from the water treatment. So we are organized in 7 technological and scientific departments. And I will now further on focus on the Department of Measurement and Automation Steelmaking, where I am responsible for. So in this department, we are developing especially measurement technologies for process monitoring and control. So we have developed, for example, a fiber-based measurement system for continuous measurement of the melt temperature in the liquid melt. A virometer system for determining, for example, the liquid core position in continuous casting, fiber-based mold temperature measurements in the continuous casting plant. And we have a very strong focus on camera-based systems, what you can see on the right-hand side. So one important part is the characterization of steel scrap by means of hyperspectral camera systems, where we can detect different types of steel scrap, and we can also detect pieces of copper or other disturbing elements in the scrap. Then we are focusing on the monitoring of the stirring process in the liquid steel treatment in the ladle, the mold cover powdering, covering in the continuous casting plant, and also furnace vessel inspections of filling degree detections. So this is the measurement part, and now I come to the monitoring and process control part by means of dynamic process models. So we have developed process models, dynamic process models for online control for all liquid steelmaking processes, also for the electric arc furnace. We use these process models also for monitoring and control of the complete process chain, as you can see here in the lower part of this figure. We combine the process models with the measurement technologies, for example, here the monitoring of the liquid bar surface in vacuum degassing in combination with the process model for degassing. And we are performing process analysis with statistical and AI methods. And now leading to the next topic, which I will focus on further, we have developed a system for scrap characterization and cost optimal calculation of discharge maps. So are there any questions so far before I go to the next topic?
I think, Bernd, we can continue, and then we can read the question when you finish, okay?
Okay. So now I will focus on the research project s-X-AIPI, which we have recently finished. The full title is called Artificial Intelligence Technologies for European Process Industry Digital Transformation. Inside this project, we had a use case, the steam-making use case, which has been performed at the electric steam-making plant of s-Nor in Spain. And I will structure my presentation in the problem definition. Then I will talk about the characterization of steel scrap with statistical methods and how we extended this by AI-driven methods. And all these tools were then integrated to a comprehensive supervision and decision support system. And finally, I will give an outlook to other similar research projects which are currently running in our institute. So first of all, the steelmaking process route at s-Nor in Spain. So here the steel is produced completely from scrap, which is sorted at a scrapyard and then charged into the electric arc furnace. They have a very sophisticated secondary metallurgy treatment with 2 ladle furnaces and 1 vacuum degassing plant and 2 different continuous casting plants for blooms and billets and 5 different rolling mills in different plants in the northern part of Spain. So the demand in this plant is clearly to characterize the steel scrap which is used in the electric arc furnace. And this steel scrap can be characterized by a high variation regarding the metallic yield, the chemical composition, and the melting behavior of the different scrap types. Furthermore, for oxidizable elements like phosphorus, chromium, or manganese, the effective element yield strongly depends on the furnace operating patterns. So the scrap properties are essential to be considered in context with the scrap mix optimization, but also regarding online monitoring and control of the electric arc furnace process, as the scrap itself influences strongly the melting behavior and the energetic and metallurgical performance of the electric arc furnace process. At s-Nor, there are steel scrap from 3 different origins is used. The first one is the most critical one. This is the post-consumer scrap. This is scrap collected from scrap cars or scrapped household systems and so on. This is a scrap which is very difficult to characterize, and the composition of the scrap is only roughly known and has a high variability. Different is it for the pre-consumer scrap. This is scrap collected, for example, in the car manufacturing industry. This scrap has a clearly defined composition and other properties. And then the last is the internal recovery scrap, which is scrap collected at the continuous casting plants or at the rolling mills in the same steel plant. And also here we have a very good assessment to the properties. So you can see here in this figure, for example, the copper content of different scrap types. And you can see that for some scrap types, the scatter in the composition and the copper concentration is very high. These are the post-consumer scraps where the copper content is can vary in a range of 0.1 1 or 0.2%, and this makes it difficult to use them in higher amounts because copper and phosphorus content have to be well known in the scrap types to avoid any quality issues, and that means you have to know these contents very exactly to allow to use also higher amounts of low-cost scrap types. So characterization of steel scrap. Here we have developed a web-based tool which allows to characterize the properties of the different scrap types which are used and provide this information for scrap mix optimization as well for model-based monitoring and control of the electric arc furnace. So this web-based tool allows a comfortable assessment of the different scrap properties, the metallic yield, the element composition, and the specific meltdown energy requirement. With the database access, we can retrieve the data of the used scrap types, the achieved meltdown analysis, the tap weight, and the energy consumption for each produced heat. And out of these data, we can apply a multilinear regression calculation, which determines the properties of the scrap types with mean value, but also with standard deviation and square value to have an indication on the reliability of the statistical determination of the scrap properties. And then the accuracy of the characterization is visualized by a graph. Here we plot the predicted versus the measured target values. Here you see an example for the electrical energy consumption. You see that the error of this prediction is quite small, and also the reliability is rather high. Of course, you always have some outliers here in the edges of this scattering dots for the different heats, but in the end, the result is quite reliable. So we can use this system also to assess the evolution of the different scrap types over time. So, for example, we can see that for certain scrap types, the copper content is decreasing or increasing, which depends on the different suppliers of the same scrap types. The quality is, of course, not equal for each scrap supplier. And with this method, you can detect all the differences between different scrap suppliers. And also, we use these scatter plots, the box plots, to see how the properties of the different scrap types scatter regarding the different element composition, for example. So what we found in our investigations is that this multilinear regression calculation provides accurate values for those elements which are more noble than iron, for example, copper, tin, nickel, and molybdenum. So for these elements, the correlation between predicted and analyzed concentration in liquid steel is very good. But for those elements which are reacting with oxygen, like phosphorus, manganese, and chromium, this correlation is much weaker. So that means that the values for the scrap composition, which are determined by the multilinear regression, are not really reliable. And this means that a consideration of further process data is required. You can see here that you have not a very good correlation between calculated and measured phosphorus concentration when using the multilinear regression calculation, which makes it difficult to to achieve the limit values for phosphorus in the liquid steel. So of course you can assess the phosphorus content in liquid steel by means of a dynamic process model, which we also have developed. And this model allows to monitor and predict the process behavior regarding all the important values of the heat status, like the melt temperature and the composition of steel and also of the slag. So the model uses an energy and mass balance calculation in combination with thermodynamic calculations for the elements which are reacting with oxygen and which are not so easy to determine. So, for example, for dephosphorylation, we have used the mass transfer limited approach with an equilibrium correlation to describe the phosphorus distribution between steel and slag, which is an important parameter for dephosphorylation. And in this highly nonlinear approach, we also have to consider the effect of lime additions and oxygen injection on the dephosphorylation kinetics and the equilibrium conditions. So you can see here that in the steel phase, as well as in the slag phase, the model allows to calculate the phosphorus concentration at the end of the AIF treatment with a very good accuracy. And this can also be used for monitoring the process behavior, but also to determine the endpoint of the process when the target values of the AIF process have been achieved and the melt can be tapped. But how shall we use this dynamic process model, which is very sophisticated, which needs a lot of analytical equations to be solved? How can we use this in a simple scrap characterization? As this is not really possible, we have decided to develop an artificial intelligence model. So we simply said that we have to consider that the phosphorus content not only depends on the contributions of the different scrap types, but also on the amount of injected oxygen in relation to the injected carbon, the amount of lime addition via the fifth hole, and also, in case it is performed, the amount of injected lime. So we know that the surplus of injected oxygen creates iron oxide in the slag, which promotes, in combination with the lime additions, the dephosphorylation reaction. So you can see here in this simple table regarding the results of different modeling approaches that when using not only the scrap data, but also in addition the parameters of the AIF treatment, like oxygen input and lime input, you can achieve a much better result regarding reliability of the prediction of the phosphorus content. And finally, we used the random forest regressor, which achieved the highest R-square value and the lowest mean average curve. Okay, so then we have a prediction of the phosphorus content by means of this AI-based model. So we can compare the calculated value to the measured one. We can see that now the accuracy has improved a lot compared to the multilinear regression model. And we can now use this AI-based model to predict the phosphorus content at the end of the treatment for each heat. And you can see here comparison between the measured values in blue and the calculated values in orange. And you can see that is a very good correspondence for most of the heats. But we also see that there are some deviations, higher deviations for some heats, which could indicate that the properties of the scrap types in use have changed. And when we do this comparison more systematically, and in case we find that this deviation between measured and predicted element content is higher than the predefined threshold for several heats in a row, which is indicated, for example, here, where we have several heats in a row with a much higher deviation than the average, then we use a so-called autonomic manager, which is also an artificial intelligence tool, to create an alarm that anomalies in the scrap type properties have been detected. And a supervision procedure then automatically activates an update of the scrap characterization to determine new values for the phosphorus content in the different steel scraps. You can see this procedure here in this scheme. So let me explain it from the top. We have the AI-based process model, which uses the scrap mix which has been charged for every heat, and other process data like oxygen input, lime input, and so on, to predict the element concentration. Then this predicted value is compared to the measured concentration, which has been determined by a laboratory analysis. And if the difference between predicted and measured concentration is higher than a threshold, an alarm is created from the autonomic manager, which says something is wrong. We assume that the composition of the charged scrap mix is not as expected, and this means that we need to recalculate the composition of the different scrap types. So this is then done automatically. A new scrap characterization is performed. We achieve new results for the phosphorus or copper concentration of the different scrap types, and an expert decides to accept or to decline these results. So if he accepts the results on the new scrap data and decides that the result is reasonable, this will cause, on the one hand side, a retraining of the artificial intelligence model, because the parameters of the AI model, of course, are based on the properties of the scrap types. And at the same time, we have to renew the calculation of the scrap mix optimization, which will, of course, calculate a different scrap mix, which is optimal for the condition of the changed scrap type composition. So, so this new result of the scrap mix optimization is then provided to the operator. He decides then to use these values or and to apply them for the next heat to be produced, so that for the next heats, this difference between expected concentration and actual concentration is below the threshold. So, as I said, we use scrap mix optimization. This is a simple simplex algorithm, although it's not as simple as it sounds, because you have to consider lots of restrictions, which are, in the first place, considering the elemental composition of the steel grade to be produced, but also further restrictions like loading restrictions, that for a certain scrap type, not more than 20 tons can be charged or something like that. And as the target value, this optimization does not only consider the scrap purchase costs, but also the cost for meltdown energy requirement, CO2 emissions, which can be assigned to the different scrap types. So this means that in the end, the scrap type, which may be cheap on the scrap market, can turn out to be expensive when considering also the cost for the required meltdown energy, for example. So at CDNOR, trials have been performed with the scrap mix optimizer, and these led already to cost savings up to 12 euro per ton, depending on the steel grade to be produced. And this was achieved mainly by increasing the percentage of low-cost scrap types in the charge mix. The better you know the composition of the scrap types, of course, the more you can allow to use scrap types which have lower costs and then also have a higher concentration of tramp elements like copper. So this is a very short video to show how the scrap mix optimization works. I will just let it run. You see here, you select the quality which has to be produced, start optimizing the scrap mix, then you will receive the result, the different amounts of scrap to be charged for the different scrap types in use. And on the right-hand side, you will see the result, the total costs, the predicted element concentration, and also further information, how much oxygen has to be used, how much lime, and so on. Yes, some words about benefits, cost savings. I already said some trials at CDNOR led to savings up to 12 euro per ton, which is of course a very high value. We did the same investigation for a lot of different steel grades you can see here, and the relative cost savings are quite positive for all the steel grades. Only for one steel grade, the scrap mixed patterns which were originally used achieved a slightly lower cost. But for most of the steel grades, this scrap mix optimization achieves more cost-efficient results. Next is the quality improvement. So what we found is when applying the system, we have fewer defects with non-conformities of the, for example, for the copper content. You see here the application of the system, and we followed it for several weeks and found that the number of conformities decreased during the application of the system. So in the end, we had an improvement of around 6%. And finally, the operational efficiency. So the AI-driven insights enable a faster and better decision for the operators and reduces the reliance on manual experience with the improved analysis of the scrap types. Yes, I want to finish my presentation with the conclusions. So, statistical models for scrap characterization provide reliable and up-to-date information on the properties of the scrap types in use. The resulting data are directly fed into a scrap mix optimization for decision support and control of the scrap mix to be charged. So as the properties of the scrap types in use vary with AIF operating conditions and also the scrap suppliers, monitoring of the deviations is required, and also an appropriate short-term reaction if significant deviations occur. So for that purpose, we have developed a comprehensive AI-based supervision and decision support system, which can detect anomalies in process and model performance caused by variations in the scrap properties, and when we apply detection, diagnosis, and self-repair modules, which I already explained. And these support the operators and engineers to ensure an optimal performance of the AIF charge mix control tools. And the whole decision support system has been implemented at the AIF plant of Sudenor in Spain and is currently tested in this industrial environment for a longer period. So we have currently we are performing two further research projects where artificial intelligence methods are used. So the first project is called IKEMIA. In this project, we use in the end the same AIF decision support and process monitoring and control tools, but here embedded in the so-called federated learning platform. So this platform will allow to have a common update of model parameters for the AIF process model with its application at several electric arc furnaces in the same company group. So on this project, we have 3 AIF steelmaking plants of one company group, and we can compare the model applications at the 3 plants, and with the common optimization of the model parameters, we can achieve overall better accuracy and process control for the 3 AIF plants. And last but not least, within a national project, we are extending the scrap characterization to predict also the effect of the scrap types on the slag composition at AIF tapping, and this will help to enhance the use of the AIF steelmaking slag for example, construction or road construction purposes. So it will be possible to avoid to find heavy metal elements like molybdenum or vanadium in the slag, which will deteriorate the use as a construction material. Yes, this is my last slide, and I thank you for your attention. And I also thank, of course, the European Union for funding the research projects which we are currently performing all around the scrap usage and the process optimization. Thank you very much for your attention. I'm happy to answer your questions which you might have regarding my presentation.
Thanks, Mr. Kleimt, for very useful and interesting presentation. And so you mentioned, so I would like to ask first, you mentioned 12 euro per ton, the optimization, the effect, yes, economic effect. So is there any room for improvement? It's just the beginning, or you feel that it's like it's already done, and or it's the room for improvement still?
I think there is still room for improvement because, as I said, we want to also to handle the effect of the scrap use on the slag, and also what has not been investigated so far, which savings can be achieved when optimizing not only the scrap selection, but also the meltdown process in the electric furnace. So having better information on the scrap composition, we probably can also control better the electric arc furnace process with the energy and material inputs, so that at the end you will also have some cost savings for energy input and for material input like slag formers or carbon input.
Okay, thank you. So we have questions. So Dr. Kleimt, thanks for your presentation and the important work you do. I have a question that might be a bit broad. Do you see a future for usage artificial intelligence in steel plants? And should these plants start paying attention to this trend, even though many are hesitant or afraid of change?
Yes, so I would say the application of artificial intelligence in steel making is very, very broad. So especially for all processes which cannot be fully described with analytical equations. And for this, the electric arc furnace is the best example, I guess. But also for other processes where process insights are difficult and where especially a lot of process data are collected and can be used to detect hidden should I say, dependencies. For example, in the product quality, you can use artificial intelligence methods to find out which of the process parameters or process operations are leading to deficiencies in your product quality. And with this detection method, you can also then find methods how to avoid these quality problems. So therefore, everywhere where either very big data are collected, a big amount of data is collected, or where the production processes cannot be described fully with analytical and mathematical equations, there the application of artificial intelligence is useful. And I could tell you numerous examples where this is already done in the steel industry.
Thank you.
Also in the downstream processes, there are many applications.
Yes, and it's a very interesting question because when we had a meeting in Belgrade with the team of s-X-AIPI project, so it was a question about the conflict of interest between workers and artificial intelligence. And so the implementation of artificial intelligence is it changed something in work because some workers has to collect data manually, and it affects their duties. And also, yes, as your colleague in this project mentioned, that people worry about implementation of artificial intelligence, and they worry that artificial intelligence will replace metallurgists or workers. And what do you think that is really it is how artificial intelligence can change the position of metallurgists, like the position of workers? So from one side, I see that workers has to make decision according to more data information. And from one side, I see that metallurgists should be more experienced, or artificial intelligence will reduce the demand for people.
So I would say that the artificial intelligence methods are a tool which help the metallurgists and the operators to do their work more reliably and more consistently. So that I mentioned it in one of the slides, that the difference between, for example, different shifts in the plant is not as high than when you use such artificial intelligence methods, because they will give then the operators tools for decision support. But in my opinion, in steelmaking, the operator always has to have the last word, because no artificial intelligence method can cover all the information which can be judged by an operator. For example, things which can only be assessed by camera technologies and which have to be decided in very short time periods. For, let's say, decisions have to be taken sometimes in 1 or 2 seconds, and nobody can wait for artificial intelligence method because before all these images are evaluated and so on. So there will always be situations where the operator has to decide, and a fully automatic steel plant running without any operator cannot be imagined, because there are too many complicated and dangerous situations in the steel plant where the operator has to have the last word. So therefore, I'm not really afraid that artificial intelligence will reduce the amount of workers or also metallurgists in the steel plant very much.
Okay, thank you. The next question. How does the interaction between the operator and the artificial intelligence system work? Is it a manual confirmation or semi-automated process? So you already answered, but so can you?
Yeah. So, normally, as I said, it's the operator still has to decide. We call it human in the loop. That means you have a control loop, but there is always, in some point of this control loop, there is the human which takes the last decision. So I showed it also here in this picture. Maybe I can show it again. Here, so the expert, he takes the decisions. If the results which are calculated by the artificial intelligence methods are really trustworthy, and because no one can avoid that this artificial intelligence methods sometimes are failing. And if you close the loop automatically, you will probably risk that some new results of the artificial intelligence methods which do not make sense in this situation will go through for an automatic control. So therefore, normally the operator has a screen where he sees some dashboards, and he gets the results of the artificial intelligence methods visualized, and then he takes the last decision: shall I trust these results or shall I discard it?
Okay. The next question, Dr. Kleimt, thank you very much for this interesting talk. In case of a lower inequality scrap, would process adjustments could be considered to upcycle even lower grade scraps? Secondly, the artificial intelligence model considers any physics-based data such as thermodynamic or dynamic.
Okay. So regarding the first question, of course, there are lots of methods to analyze the composition of scrap, and also to detect disturbing elements inside the scrap. And also these methods can be camera systems, or, for example, the laser-based laser-induced spectroscopy. The LIP system allows to analyze the composition of the scrap on the surface, and based on these analysis methods, there are sorting procedures. In the best case, there will be a robot which is controlled by the sensor, and this robot will pick up the disturbing scrap elements out of the scrap stream and will put them away so that they are not charged into the furnaces. Secondly, we can, of course, use the shredder plant. So in this case, it's a kind of mechanical sorting, so that disturbing parts in the scrap, like plastics or organics, are sorted out by mechanical methods. This is also a good possibility to use also low quality scraps. Of course, it's a higher effort. You have to put in that to improve the quality of the scrap before it is charged to the furnace.
Thank you. And sorry.
The question is, so there are new artificial intelligence methods which are to introduce also analytical equations or physical modeling knowledges. So, for example, we have the physics-infused neural networks, which can consider also analytical equations if they are already known and if they are well established. It doesn't make sense to use, for example, a neural network when you already know quite well the connection between input and output data. But there are more and more methods which combine the analytical knowledge with the artificial intelligence methods. So this is a new development in AI, which is improving more and more.
Thank you. And Mr. Kleimt, as I understand, to implement artificial intelligence in steel industry, there are a lot of sensors working correctly required, because when we visited steel mills, we see that many information cannot be collected in a proper way. For example, some weight is not working. Steel workers, operator doesn't understand what exactly weight of the charge material to the furnace. So as in the sense, there are a lot of like sensors, additional sensors has to be implemented to the production. Yes.
Yeah, that's correct. So what is the information which is not available as data, which can be stored and which can be analyzed by artificial intelligence methods? This information is, of course, not really usable for monitoring, controlling, optimization of the processes. And also failures in data. So when data are sometimes missing or there are faulty data, can disturb artificial intelligence methods. However, there are also sophisticated filter mechanisms which can sort out the faulty data so that they are not leading to false results of the artificial intelligence application. But you are completely right. If you have no sensors, you will have no data. And if you have no data, you cannot apply artificial intelligence. That's the true story. Yeah. And the more data you have, of course, the better is the result of the artificial intelligence method.
Thank you, Mr. So, and the last question. So we have some participants from steel mills, and the recording will be watched by people, workers, metallurgists from steel mills. So, as I understand, this product can be provided not only in the European Union and also to other countries if some clients will ask you to work with this project with them.
Yes, that's correct. So normally, when we have finished a research project, we are allowed to further use, or we are even obliged to further use the results to use them in industrial applications. And this, of course, also allows us to apply the methods in countries outside the European Union.
Mhm.
Of course, in every case, we have to decide. So you know well that at the moment there is a little bit that how should I say it in a good way. So I think the relations between European countries and other countries are not always very good
Mhm.
like this. And of course, there might be restrictions, but it's not in this way that what we have developed in the European research project is not only for European countries.
Okay. Thank you, Mr. Kleimt, for your time. I know that you are very busy, and I appreciate that you shared this very interesting information presentation with the audience. And I hope that it will help you also to go further in this project to achieve new results, new targets. And I wish you all the best. And thanks for participants, for audience. Please stay in touch, and next Wednesday, the same time, 5 p.m., we will have interview with Berhard Wischka. He will join us again, and now we will speak. He will share not presentation, but we will speak about the future of steel making, and we can ask some more, let's say, not personal question, but I would like to discuss about the future in steel making process. Again, thanks, Mr. Kleimt. I wish you all the best and hope to see you.
Yes, thank you, Mr. Korblin. Thank you, everybody, for your very good questions, and thank you very much for your attention, and all the best to you and your
Thank you.
work in this new plant.
Okay, thank you. Bye-bye.
Bye-bye.
Bye-bye.